right. What is up, everybody? Tom McGurl here for another Learn Rust live stream. Tonight we're going to be doing chapter 15 of the Rust programming language book. So I hope you're excited. I'm excited. We're going to be learning about smart pointers, which is a new topic for us, something we've never covered, obviously, but should be really fun. But yeah, if you're watching on YouTube, thank you for watching. If you're watching on Twitch, feel free to hop in the chat and leave any questions or comments you have there. And if you're watching on YouTube, put some comments down below in the video. Always love to answer any comments. We've been getting some great feedback on the stream. So been really excited. Just a lot of people messaging and saying they're really enjoying it. So that's fantastic. I'm super glad that people are benefiting from it. I'm definitely benefiting from it. I'm learning Rust, right? So can't complain there. All right, so as usual, we got to kick it off with the usual plugs. All the YouTubers out there, you know when to fast forward. You're like, oh, fast forward, I got it. It's fine. That's fine. But we got to do it. So if you've missed any of the previous episodes, do not worry. They're all here up on YouTube for you in the video section. Just go to YouTube and search my name, Tom McGurl. These will come right up. You could also probably search Learn Rust Together, and they should come up as well. But yeah, we got all the chapters of the book, chapters 1 through 14 here, as well as the rustlings exercise. We took a little break after chapter 10 to go through the rustlings exercises, which were a really fun way for us to flex our muscles and use some of those skills we learned throughout the book to solve some of those problems. We also have some one-off content, building a development environment for Rust with Docker using Docker Compose. That's going to allow you to work on Rust without having to install it, right? And you can have a repeatable environment on different machines. So definitely check that out. It's a little short one. Before that, we did some other stuff as well. We got building a live serverless API with AWS Lambda, using TypeScript, using DynamoDB as a database, which is a native to AWS database. It's a non-relational database, so that was pretty great. And we used S3 for that as well. Before that, we did some React Native stuff. So jumping around a lot. Obviously, I come from a front-end background more so, definitely more experience there. So the early content is going to be focused on that, but now it's all about Rust, right? It's all about Rust. Just a heads up, next week I will be taking a break just for 1 week because I'm going to be redoing the office. We got some new carpet coming in. This green, off-green, weird mucusy colored carpet's going to be going out. We'll get some nice dark colored carpet, a new chair, doing some upgrades, right? Doing some upgrades. We're going to do a little crate install in the office, so looking forward to that. But don't worry, I will replace that stream with a new video, one-off video. We're going to be making a API request, asynchronous request with Rust. So I'm going to do a little one-off video. I'll get that up over the weekend. Maybe I'll stream that as well, and then I'll have that posted for you next week, just in case you're like, oh, where's my content? You're going to have it. Don't worry. Don't stress. As always, check out the Twitter. Give a follow there. You'll get notified when I go live. Obviously, if you subscribe on YouTube, you'll get notified when new content's pushed up. But yeah, follow Twitter. I'll be posting stuff. If I post new content, you'll see it there as well. And today, we also will be pushing, as usual, all of our code up to our GitHub repo. We have the Learn Rust Live repo here. This is going to hold all of our chapters that we've done so far. You can see the commits are broken down by chapter here. So go in there. If there's a particular chapter that's of interest to you, you can also just go into the projects and you'll see the chapters broken down here as well. Last week we did 14, and you'll actually see a workspace because that's what we used for this. We used a little workspace setup. So definitely check that out. Follow along if you want. You can pull down the code. You can comment. You can star it if you want. No one started. I'll star it. There you go. We got 1 star. Come on. But check that out. But today we're going to do chapter 15, and you know how we always kick these sessions off. We always got to give a shout out to the authors. So huge shout out to Steve Klobnik, Carol Nichols, and anyone from the Rust community that has contributed to this book. As usual, if you've watched these videos before, you know that we have them to thank for this, right? Couldn't be doing this without them. This book, just the mere fact that it's free, right? And it's out there, it's a free resource, really has been amazing. It's allowed us to learn Rust without having to invest anything. It's also allowing me to stream it, right? If it was a paid book, I couldn't be out here just putting out someone's paid content for free for all of you. So it's great that this is freely available. Check it out if you haven't already. If you've been following along, you've already checked it out. And again, today we'll be doing chapter 15. So once again, as always, huge shout out Steve Klobnik, Carol Nichols, and anyone who's contributed to this fantastic resource for our path into becoming Rustaceans, right? We're slowly, I know I'm like, my claws are growing. Becoming a Rustation. I'm pretty excited about it. But today, what's it about? Smart pointers. Now, I'm excited. I'm scared, but I'm excited. Why am I scared and excited? Well, pointers are always something that when I hear it, I'm like, oh, it reminds me of C, right? Flashes of C coming back at me, a little PTSD from my C days back in college. But we're going to dive in. We're going to read it. We're going to absorb this material. And we're going to try to, get some use out of it. We've come across the smart pointers a little bit in our Rustlings exercises. Clam Watson in the chat's come across smart pointers. He knows the deal. But yeah, so today we're going to go through this, and this is why, so like we've talked about this a few times, but I want to like reiterate, usually I'm one that just jumps in. I try to jump in and write some code, but with Rust, I feel like having this backbone and this kind of resource to get a better understanding of the language before jumping in has been extremely valuable and important. If I were to jump in and see smart pointers, I would have no idea. So that's why we're going to read about it. We're going to learn about it. We're going to do the exercises and figure things out. And then I took a little peek ahead in the book. I didn't read anything, but I just took a peek at some of the chapters, and it looks like we're going to be getting into object-oriented. Not a huge fan, but we'll see. Not a huge fan. More of a functional guy, but we'll see. We'll see. Patterns and matching, which sounds awesome. But really, one of the cool things I saw was Chapter 20 is a final project, building a multi-threaded web server. So that's going to be super exciting. It's going to help us leverage everything we've learned in our journey along the way. So I'm really excited to get there. To be honest, I didn't know if we were going to get this far. I didn't know how long, we were going to go through this, but it's been really fun. And thank you for coming along on the journey. It's been amazing to see people viewing all of the videos, right? These are long videos. It's a big time sink for all of you. So really awesome to see the regulars coming back to the YouTube channel to view those videos. And I really hope you're enjoying this journey as much as I am. All right, let's hop in. We'll pull up smart pointers when we need to. I will pull up I have the code base here. So we'll pull that up. Well, let me close that. We'll pull that up when we need to. I'll dock it over here. But let's jump in. Let's talk about smart pointers. All right, so a pointer is a general concept for a variable that contains an address in memory. So we talked about this before, right? A pointer points to an address in memory. So if you imagine your memory as contiguous blocks of memory, right, of addresses, a pointer points to the address. So think about it like this. One way I like to think about it is a pointer is like the address of a house. It's not the house or what's in the house, the rooms, the content, the people, the pets. It's just the address to the house, right? It's just a pointer to the address. So it's a general concept. This address refers to or points at some other data, right? The most common kind of pointer in Rust is a reference, which you learned about in Chapter 4. References are indicated by the ampersand symbol and borrow the value they point to. They don't have any special capabilities other than referring to data. Also, they don't have any overhead and are the kind of pointer we use most often. So references we've seen a lot of, right? We pass them. Why do we pass references? Well, for attributes or variables that don't leverage the copy trait, we use references as a way to pass information to functions without having that function take ownership of that information. So if I create a variable or a struct, like a point with an x and y coordinate, and I want to pass that point to a function, but still be able to use the point after the function has closed, I would pass a reference to that function so that that function doesn't take ownership over that structure, right? This isn't the case with, as I mentioned, things that implement the copy trait, such as basic strings such as integers, unsigned integers, 32-bit integers, and characters. Those have the copy trait. But for other functions and constructs, right, we would pass a reference. Smart pointers, on the other hand, so these are different than regular pointers, different than references, are data structures that not only act like a pointer, but also have additional metadata and capabilities. The concept of smart pointers isn't unique to Rust. Smart pointers originated in C++ and exist in other languages as well. In Rust, the different smart pointers defined in the standard library provide functionality beyond that provided by references. One example that we'll explore in this chapter is the reference counting smart pointer type. This pointer enables you to have multiple owners of data by keeping track of the number of owners, and when no owner remains, cleaning up that data. What does that mean? We pass things around, and when you pass something to a function without a reference, it becomes the owner, right? This is going to allow us to pass something to multiple owners, and then we'll clean that data up when all of the owners have released it, right? So we've already encountered a few smart pointers in this book. In Rust, which uses the concept of ownership and borrowing, an additional difference between references and smart pointers that references are pointers that only borrow data. In contrast, in many cases, smart pointers own the data they point to. That's pretty interesting, right? They actually own the data. We've already encountered a few smart pointers in this book, such as string and vector. In Chapter 8, Although we didn't call them smart pointers at the time, both these types count as smart pointers because they own some memory and allow you to manipulate it. They also have metadata such as their capacity and extra capabilities or guarantees, such as with string, ensuring its data will always be valid UTF-8. So that's interesting, right? So strings will make sure their values always have valid UTF-8. Smart pointers are usually implemented using structs, which we've seen, right? We created point structs. We created a struct to represent an IP address. So we've done a bunch of structs throughout our pathway here. The characteristics that distinguish a smart pointer from an ordinary struct is that smart pointers implement the deref and drop traits. The deref trait allows an instance of the smart pointer struct to behave like a reference so you can write code that works with either references or smart pointers. The drop trait allows you to customize the code that is run when an instance of the smart pointer goes out of scope. All right, let's read that again because this is important, right? The deref trait allows an instance of a smart pointer struct to behave like a reference, so you can write code that works with either a reference or smart pointer. So deref is going to allow you to leverage smart pointers just as you would a reference pointer. The drop trait allows you to customize the code that is run when an instance of a smart pointer goes out of scope. In this chapter, we'll discuss both traits and demonstrate why they're important to smart pointers. Given that the smart pointer pattern is a general design pattern used frequently in Rust, this chapter won't cover every existing smart pointer. Many libraries have their own smart pointers, and you can even write your own. We'll cover the most common smart pointers in the standard library. Woo, let's see. Box. We've seen box. We saw box in Rustlings, so I'm excited about box. Box over the generic type T for allocating values on the heap. RC over the generic type T, a reference counting type that enables multiple ownership. Ref over the generic type T, and ref mutable reference over the generic type T. Access through ref cell over the generic type T. A type that enforces the borrowing rules at runtime instead of compile time. Ooh. In addition, we'll cover the interior mutability pattern where an immutable type exposes an API for mutating an interior value. We've done a little something similar. So you may remember that we've created structs that have private properties, and we've exposed ways to mutate those properties in a public way. So this is going to be similar to that, but we're going to expose immutable types with the ability to mutate them through a separate, a separate API. We'll discuss reference cycles, how they can leak memory and how to prevent them. Let's dive in. Let's do it. All right, using box T to point to data on the heap. Remember, things can be allocated on the stack or on the heap, right? The most straightforward pointer is a box, which type is written as box over the generic type T. Remember, when we see this, we say, whatever this is, it's generic over the type in here, T. In this case, T just represents generic type, so it could be string, character, integer, whatever you want, right? Boxes allow you to store data on the heap rather than on the stack. What remains on the stack is the pointer to the heap data. Refer to chapter 4 to review the difference between the stack and the heap. So we've talked about that before. You can, if you want to, chapter 4, it's here. It's right here. Ownership. I'm wearing a hat in this video, so you know it's good. You know my hair wasn't. All right. Boxes don't have performance overhead, other than storing their data on the heap instead of on the stack. So boxes don't have performance overhead other than the fact that they store their data on the heap rather than the stack, which we know is a slight performance hit, right? But they don't have many extra capabilities either. They're pretty simplistic. You'll use them most often in these situations. So let's see what they are. First one, when you have a type whose size can't be known at compile time, and you want to use a value of that type in a context that requires an exact size. So you don't know the size of the thing at compile time, but you want to use it, right? You want to use it in a type, you want to use it in a context that actually does require it knows the size. The second case is when you have a large amount of data and you want to transfer ownership, but ensure the data won't be copied when you do so, because that could incur a cost, right? And the third is when you want to own a value and you care only that it's a type that implements a particular trait. So when you want to own a value, but you don't care what kind it is, as long as it implements a particular trait rather than being of a specific type. So you don't care that it's a character, you don't care that it's a integer, you just need it to implement the copy trait, for example. We'll demonstrate the first situation in the enabling recursive types with boxes section in the second case. Transferring ownership of a large amount of data can take a long time because the data is copied around on the stack. To improve performance in this situation, we can store the large amount of data on the heap in a box. The only small amount of pointer data is copied. Then only a small amount of pointer data is copied around on the stack, while the data it references stays in one place in the heap. So rather than copying a whole contiguous chunk of data around, you're just copying the reference to it so that the data remains in one place, right, on the heap. The third case is known as a trait object, and Chapter 17 devotes an entire section called Using Trait Objects that allow for values of different types, just to that topic. So we're going to cover that in Chapter 17. That's 2 chapters away, right? Just for that topic. So what you'll learn here, you'll apply again in Chapter 17. Awesome. I think we've just committed to making it all the way to Chapter 17. Using a box to store data on the heap. Before we discuss the use case for box T, we'll cover the syntax and how to interact with values stored within a box. All right, so what I'm going to do is I'm going to pop this over here, and I'm going to create a new Chapter 15 folder here. So we have our projects folder, and here's where we have all of our folders that represent the chapters. So I'm going to just make a new one, Chapter 15, and we're going to call it Smart Pointers. We'll go ahead and go into Smart Pointers here, and we'll just make a new, we'll do a cargo new, and we'll call it box. It can't be used because it's a rest keyword. All right, so we'll call it cargo new box type. All right, we'll go into box, and I'm just going to go ahead and open a new one, code box type. So we got our Rust analyzer, which you know we're all about these days. We're all about the Rust analyzer. All right, so what do we have in our folder here? So we have our source, we have our main. There we go. Okay, so let's go ahead and copy what they've written here on the left. So what are we gonna do? We have our main function. We're gonna say let b equal box, and this is similar to like your new string syntax. We're gonna do box new 5. So we're storing an assigned 32-bit integer, which is the default. And you can see here in my Rust analyzer, it's showing new is gonna take, in this case, because we specified it's 5, it's gonna take it as a signed 32-bit integer, right? And I can probably specify that it's not if I wanted to, but we're gonna go with it. Okay, and then we're gonna do print ln b equals, and then b. All right, I'm just gonna run cargo run, we'll see what we get. So b equals 5, cool. We define the variable b to have the value of a box that points to the value 5, which is allocated on the heap. This program will print b equals 5 in this case. We can access the data in the box similar to how we would if the data were on the stack, just like any owned value, right? When a box goes out of scope, as b does at the end of main, right? At the end of main, b is out of scope, it will be deallocated. The deallocation happens for the box stored on the stack, and the data it points to is stored in the heap. So it's actually two deallocations happening, one for the box, which is stored on the stack, and one for the actual data that it points to, which we're storing in the heap. And again, we could just say b equals 5, and that would just allocate 5 to the stack, but doing it with the box is actually allocating the data to a spot on the heap while the box itself is on the stack. So that's the clear difference here. Putting a single value on the heap isn't very useful, right? We don't need to do this. We could just say let b equal 5. So you won't use boxes by themselves this way very often. Having values like a single signed 32-bit integer on the stack, where they're stored by default, is more appropriate in the majority of situations, right? So that would be let b equal 5. Let's look at a case where boxes allow us to define types that we wouldn't be allowed to do if we hadn't used boxes. So let's see, this obviously we could replace this code. What it's saying is we could replace this code with this, right? We could do let b equal 5. And this would all still work, and actually it's preferred. So we're gonna see now instead how to actually get the benefits that box is gonna provide us. Enabling recursive types with boxes. At compile time, Rust needs to know how much space a type takes up. One type whose size can't be known at compile time is the recursive type, where a value can have as part of itself another value of the same type. Let's think about an example, a linked list, right? So a linked list, you have a node, and the node might have, excuse me, I'm gonna sneeze. Excuse me. Woo. So you might have a node in a linked list. And so that node is gonna have its value, and then it has a pointer. And what does that pointer point to? It points to another node. And I don't mean a pointer like in Rust, I mean a second property. So you imagine a node that has a value, and then maybe a next property, and that would point to another node. So that would be a recursive type. The const list type we define is straightforward except for the recursion. Therefore, the concept in this example will work with, the ones we'll work with will be useful anytime you get into more complex situations involving recursive types. All right, so let's see about the cons list. A cons list is a data structure that comes from the Lisp programming language and its dialects. So if you're not familiar with Lisp, you may have come across a Lisp. A Lisp is a list processing language. So its syntax looks a lot different than something like this. You'll have a lot of parentheses, and it'll be lots of lists of arguments and lists of functions. One great example that's very popular now is the language Clojure. So Clojure is a Lisp. It runs on the Java virtual machine. It's a very powerful language, often used to write, if you want to use software that runs on the Java virtual machine. One popular example is Kafka, right? A queuing system or stream processing library. Kafka runs on the JVM, so sometimes you'll see people write Kafka consumers and producers using Clojure, or anytime you want to avoid Java. It's another great use case, and that would be a Lisp. And you'll see, lots of parentheses, right, and nested. So it's pretty crazy, but they're also very popular and they're very functional. Okay. In Lisp, the cons function, short for construct function, constructs a new pair from its two arguments, which usually are a single value and another pair. These pairs containing pairs form a list. So the pairs containing pairs form a list. So if you think about it, it's like something like this, right? Right? So this is a pair that contains a pair, right? Something like that. Okay. The cons function concept has made its way into more general functional programming jargon. To cons X onto Y informally means to construct a new container instance by putting the element X at the start of the new container, followed by the container Y. So to cons X onto Y. So you probably, if you're like me, you've been at a bar or you've been at a restaurant, you're having a drink, and you just overhear casual conversation, and someone just says, to cons X onto Y. It happens all the time, right? I hear this in the subway, and now this is what they're talking about, right? Talking about putting the element X at the start of the new container, followed by the container Y, obviously. We knew this already, right? Each item in a cons list contains two elements, the value of the current item and the next item. So just like a linked list, right? That's what we're talking about here. I just said this, right? Value of the current item, next item. The last item in the list contains only a value called nil. So it's almost like iterators, right? Where iterators have a next until they have nil, right? Until you hit the end. A cons list is produced by recursively calling the cons function. The canonical name to denote the base case of this recursion is nil. What does that mean? Basically, the base case is when you reach the end, right? You've reached the end of the recursion when you get to nil. Note that this is not the same as the null or nil concept in chapter 6, which is an invalid or absent value. This is different, capital N, which means the end, right? Although functional programming languages use cons lists frequently, the cons list isn't a commonly used data structure in Rust. Most of the time when you have a list of items in Rust, vector T is a better choice to use. So a vector is a better choice to use. Other more complex recursive data types are useful in various situations. But by starting with the cons list, we can explore how boxes let us define a recursive data type without much distraction. Pretty cool. So the listing below contains an enum definition for a cons list. Note that this code won't compile yet because the list type doesn't have a known size, which we'll demonstrate. All right, so let's do it. Let's go ahead and add this enum. And it's going to have a cons of a signed 32-bit integer and a list. So recursive, this is a recursive type, right? List is the enum, and this contains a list. So this is what we mean by a recursive type. And of course, nil, which means the end there. All right. And you can see here, they mentioned it won't compile, and you'll see in my Rust analyzer that it won't compile. Recursive type list has an infinite size. Cool. Using the list type to store, okay, wait, so first let's say, note, we're implementing a cons list that holds only signed 32-bit values for the purposes of this example. We could have implemented it using generics, as we discussed in chapter 10, to define a cons list type that could store values of any type. So we could have done but we're just demonstrating it like this. Using the list type to store the list 1, 2, 3 would look like the code in listing 15.3. So we're going to go ahead and pull in. This is if we have create list, we can do let list. In our case, we can do list cons 1, cons 2, cons, and so you can see the parentheses. So we're getting into that lispy looking stuff, right? Oh, sorry, I have to do. And nil here, it's saying cannot find the value nil in this scope. I think that's okay for now. Oh, because it's list nil. And that's probably why they have this here. Right. So this is the list type, but if we just import the crate here, we can use it like that. So let's copy this. And then we can get rid of this. And then we can get rid of this. Okay, what is this saying? It's probably saying that's not a dependency. We'd have to add that crate to our cargo. So we will, for now, we'll just go back to this just so we can see it compile. I'm just gonna comment this out. So it's basically saying we're just implementing something that's already basically implemented in that crate. Okay. Using the list enum to store 1, 2, 3. The first cons value holds 1 and another list value. This list value is another cons value that holds 2 and another list value. This list value is one more cons value that holds 3 and a list value, which is finally nil, the non-recursive variant that signals the end of the list. If we try to compile this code, we will get the following error. So you can see here the error that they're saying is recursive type has infinite size, and we can see that simply by hovering over our enum list here. Okay. The error shows this type has an infinite size. The reason is that we've defined list with a variant that is recursive. Again, a list containing a list. It holds another value of itself directly. As a result, Rust can't figure out how much space is needed to store a list. Let's break down why we get this error a bit first. Let's break down why we get this error. First, let's look at how Rust decides how much space it needs to store a value of a non-recursive type. So let's try to look at what it does in the case when we don't have a recursive type, how it determines how much space it needs. So recall the message enum we defined in listing 6.2, so chapter 6, when we discussed enum definitions. So we have a message that has quit, move, write, change color. To determine how much space to allocate for a message value, Rust goes through each of the variants to see which variant needs the most space. Rust sees that message quit doesn't need any space. Message move needs enough space to store an integer 32, right? It needs to store 2 integer 32s. Quit stores nothing, move stores 2 integer 32s, right? And so forth. Because only one variant will be used, the most space a message value will need is the space it takes to store its largest of its variants. In this case, the largest variant is this, change color, which stores 3 32-bit integers, right? Contrast this with what happens when Rust tries to determine how much space a recursive type, like the list enum in 15.2 needs. The compiler starts by looking at the cons variant, which holds a value of type integer 32 and a value of type list. Therefore, cons needs an amount of space equal to the size of an integer 32 plus the size of a list. To figure out how much memory the list type needs, the compiler looks at the variants, starting with the cons variant. Cons variant holds a value type integer 32 and a value type list, and so forth, recursively, on to infinity. And this is demonstrating it, right? Using box T to get a recursive type with a known size. So we can't use it like this. We don't have a known size, it's a problem, right? It won't let us do this. Rust can't figure out how much space to allocate for recursively defined types. So the compiler gives the error in listing 15.4. But that error does not include this helpful suggestion. The error does include it. Let's see if we see that error in our Rust analyzer. Okay. It says here, insert, oh, sorry, let me pull that back up. Insert some indirection, right? Not misdirection, indirection. Example, a box, a reference counting pointer, or a reference to make the list representable. Interesting. In this suggestion, indirection means that instead of storing a value directly, we'll change the data structure to store the value indirectly by storing a pointer to the value instead. Yeah. Little indirection, right? Little indirection. Pretty cool. Because box over the generic type T is a pointer, Rust always knows how much space a box needs. It needs the amount of size for a pointer, right? It needs pointer size, doesn't change based on the amount of data it's pointing to. The pointer will always have the same size. This means we could put a box T inside the cons variant instead of another list value directly. The box T will point to the next list, and we know how big that size is. You see what's going on here? I'm gonna try to describe it with stuff on my desk. All right, I've done this before. You ready? We got a skateboard, right? A tech deck. We got one. We got a cons list. It's made of a tech deck and a list of skateboards. Now, we don't know how big this is. We just know it's another list of skateboards. So we don't know the size, right? This could be anything. What if instead of storing the list, we store a pointer to the list? So I'm going to put that list over here. And instead of storing, so here's my list. Instead of storing this list, I store a pointer to that list. We know the pointer has a particular size. So we know that the size of my structure here is just the size of this and the size of my hand. We don't care about the size of this yet. So we can infer a size. I hope that helped. It probably didn't, but I got to show off my tech decks again, which you all know I love doing. Okay. So conceptually, we still have a list created with lists holding other lists, but this implementation is now more like placing the items next to one another rather than inside one another. I love that. It's more like placing them next to each other, which I did. I did that, right? I did that with my tech decks. I showed it. It was next to each other rather than inside each other. We can change the definition of list enum in 15.2 and the usage of the list in 15.3 to the code in listing 15.5, which will in fact compile. So also, I'm going to copy this, and I'm going to do this because I understand now what is happening here. It is allowing me to use the enum defined there in shorthand, which I love. Okay, so let's put a box. So what we'll do here is this, instead of being a list, it's going to be a box. It's going to be indirection, right? A box around the list. And then down here, you'll see complaints. And the complaints are saying, store this in the heap by calling box new. So instead of just having cons, we're going to say box new. And it may look a little bit funky, and we're going to have a lot of parentheses, and that's why it's looking like a Lisp. Do 3 kickflips. Challenge accepted. You can't see it, but I'm going to do it. 1, 1, 2. I dropped that one. 3. I did it. I promise you I did it. Okay, so this is where it's getting lispy. You're seeing these parentheses, and now you know what I'm talking about. I told you it's going to be a lot of parentheses. I didn't lie. And actually, to compensate for that, you can color code your parentheses. Usually when you're dealing with a Lisp, you'll color code your parentheses so that you can match up which ones go with what. It's pretty cool. Just like HTML, sometimes if you're working the front end, you'll do that. And there we go. We have enough parentheses. It's stretching out into Neverland. But there, I know it's a little small, but you can at least see what's going on there, right? And we can even, right, we could probably do something like this. But that would be crazy. But usually with a Lisp, you do end up doing stuff like this, right? Box new. So box new, cons. We'll probably throw this up here like this, box new, right? Move this over here. Put the box new up here, right? Put our nil down here. Gets crazy. That's what Lisp look like. That's what Clojure looks like. It's nuts. I'm telling you. So we change the definitive list to the below, and it will compile. The cons variant will need, the cons variant will need the size of a signed 32-bit integer plus the space to store the box's pointer data. The nil variant stores no values, so it doesn't take any space. And again, we only look at what takes up space, and we go off the most space consuming for to figure out the size. That's what Rust is going to do. So the nil value stores no values, it needs no space other than the cons variant. We now know that any list value will take up the size of the signed 32-bit integer plus the size of a box's pointer to data. By using a box, we've broken the infinite recursive chain so the compiler can figure out the size it needs to store a list value. Below, we see how that's represented. So we went from something like this to replacing this inner piece here, this inner cons after the 32, to replacing that with indirection to a pointer to something else. So that's really cool. Boxes provide only the indirection and heap allocation. They don't have any other special capabilities, like those we'll see with the other smart pointer types that we're going to see in a minute. They also don't have any performance overhead that these special capabilities incur, so they can be useful in cases like the cons list, where the indirection is the only feature we need. We'll look at more use cases for boxes in chapter 17. So they're good for cases where we need indirection. Love it. The box T type, so the box over generic type T, is a smart pointer because it implements the deref trait, which allows the box over the generic type T values to be treated like references. So when a box T value goes out of scope, the heap data that the box is pointing to is cleaned up as well because of the drop trait it implements. Let's explore these two traits in more detail. These two traits will be even more important to the functionality provided by the other smart pointer types we'll discuss in the rest of the chapter. All right, let's find out. Look at this. We're going to find out about treating smart pointers like regular references with a deref trait. All right. Excuse me. Implementing the deref trait allows you to customize the behavior of the dereference operator. We've used this, the ampersand, right? Let me zoom in there. Let me make sure you can all see that. We've used that, right? To dereference it, to get the value that the reference is pointing to. So a deref trait is going to allow us to customize the behavior of that. Pretty cool. As opposed to the multiplication or glob operator. It's not the multiplication operator. By implementing deref in such a way that a smart pointer can be treated like a regular reference, you can write code that operates on references and use that code with smart pointers as well. Let's first look at how the dereference operator works with regular references, using the ampersand. Then we'll try to define a custom type that behaves like a box and see why the dereference operator doesn't work like a reference on our newly defined type. We'll explore how implementing the deref trait makes it possible for smart pointers to work in ways similar to references. Then we'll look at Rust's deref coercion feature and how it lets us work with either references or smart pointers. Rust is chock full of features right now, right? It's crazy. And the interesting thing, just a quick aside, is we're reading the book, right? We're not building something right now. We're reading the book, so we're getting all of this info. And it may not occur to us right now what its use is. We did see one use, building a cons list, but we didn't see the use of the cons list itself. But we did see how these things are used. But this is one of those things where you're going to come across something while you're writing your program, and it's going to click, and you're going to say, that's what I need. And how are you going to know you need it? Because your compiler is going to tell you. I always think of the example of generic types, just generally, right? Generic types. When do we need a generic type? You don't really know until you hit that use case, and then you're like, here's where I need a generic type. For example, think about something like when you're implementing API, and you want to allow people to hit your API asynchronously. So you know that whatever your API returns has to return something that can be dealt with in an asynchronous way, like a promise, right, or a future. And so you can make your function generic as long as the thing it's dealing with can be handled like a promise or a future. Or maybe you want to be able to multiply two things. You don't care what they are. You just care that they are able to be multiplied. So you make it generic, right? And so the same thing here. We're going to see where these use cases lie as we start to build things out. And I'm excited for chapter 20 because I think when we actually build that web server, we're going to really leverage some of this stuff. Okay. So there's one big difference between my box T that we're about to build and the real box T. The OG standard library version, like the original gangster version. We're going to build like the low-key young thug version, but we're talking about the original gangster version. Our version will not store its data on the heap. We're focusing this example on deref. So where the data is stored isn't very important. We don't care about that right now. It's an implementation detail. Following the pointer to the value with the dereference operator. So following the pointer to its value. So we remember an address, right? It's actually going to the address, putting the address in your GPS and taking it to get to the house, right? Or the brewery. Maybe you're going to a brewery, maybe you're going to a winery. Maybe you're going to a party. Not during COVID. It's been years. Feels like years. All right. So a regular reference is a type of pointer. And one way to think of a pointer is this an arrow to a value stored somewhere else, like my hand pointing to something else, right? In listing 15.6, we create a reference to a signed 32-bit value and then use the dereference operator to follow the reference to the data. Let's do it. So I'm just going to, I'll create a new one for this. What's this chapter? Let's see. We'll talk about deref trait. So what we'll do is I'll just go up a little bit here. Cargo new, deref, and what was the other trait? What was the other trait? What was the other trait called? It was, well, I guess we're just talking about deref in this case. So we'll just do that. Yeah, we're just talking about deref. So I'm going to just do deref trait. All right. Put this over here. Main. Okay. So let me type this out here. And again, pointer is an arrow. So a regular reference is a type of pointer, as an arrow to the value it's stored. We're going to create a reference to a signed 32-bit value and then use the dereference operator to follow the reference to its data. So we're going to start out, we're going to do let x equal 5. Again, we're not using a box here. We're going to allocate this on the stack. Let y is going to be a reference to x, which we know because of the ampersand there, right? And we're going to assert equal 5 comma x. So x is not a reference, x is the actual value, so we're going to assert that that's true. And then we're going to assert that 5 equals what happens when we dereference y. We get the value from it, right? We follow that arrow to its value. The variable x holds a signed 32-bit value 5. We set y equal to a reference to x. We can assert that x is equal to 5. However, if we want to make an assertion about the value in y, we need to use the asterisk y to follow the reference to the value it's pointing to, hence the dereference represented by the asterisk. Once we dereference y, we have access to the integer value y is pointing to that we can compare with s. If we tried to write assert 5y instead, we would get a compilation error. So right now I'll just run this and you can see there's no errors, right? But if I tried to do it without the dereference, you see we get an error. No implementation for integer equal. So you can't compare and use partially quality on an integer and a reference to an integer. So, and we've seen this, right? We've dealt with this before. It's just going into a little more detail. Comparing a number to a reference to a number isn't allowed because they're different types. We must use the dereference operator to follow the reference to the value it's pointing to. Okay. Using box like a reference. We can rewrite the code in listing 15.6 to use a box instead of a reference. The dereference operator will work as shown in 15.7. So we're going to, instead of using a standard reference here, or what we would call just a regular pointer, we're going to use a box. So we're going to do box new, and we'll do that over x there. We'll clear and run this code, and you'll see everything compiles. So we're still good. The only difference between this listing and what we had before is that we set y to be an instance of a box pointing to a copied value of x rather than a reference pointing to the value of x. In the last assertion, we can use the dereference operator to follow the box's pointer in the same way we did with the standard pointer reference that was y before. Next, we'll explore what is special about box that enables us to use the dereference operator by defining our own box type. So, defining our own smart pointer. I'm a smart pointer. You're a smart pointer. Are you out there pointing? You're probably a smart pointer. Let's build a smart pointer similar to box over generic type T. Type provided by the standard library to experience how smart pointers behave differently from references by default. Then we'll look at how to add the ability to use the dereference operator. The box T type is ultimately defined as a tuple struct with one element. So listing 15.8 defines myBoxT type in the same way. We also define a new function to match the new function defined on box T. So it's going to be similar, but again, it's storing it not on the heap, it's storing on the stack, but that's okay. Implementation detail, that's not what we're caring about. It's not the focus. Relax. All you be in the chat and in the comments, but it's... We saw the note. All right. So defining my box. So let's do it. My box. All right, let's go up here. We're going to do struct my box generic over type T. Oh, what was that? That was recursion right there. T. It just contains a T. That's all that is. It's the same as doing this, right? Know what I'm saying? Okay, anyway. And so we have our implementation block. We specify that we have my box T. And we're going to create a new function so that we can use it in the same way we use box new. And so it's just new. It's going to take X. X has to be of type T. We know that. And it's going to return itself, right? So it's going to return my box generic over type T. And all it's going to do is it's going to initialize a my box with T, whatever you passed it, which is X, right? Where it's going to initialize it with X. Okay. We define a struct named myBox and declare a generic parameter T because we want our type to hold a value of any type. The myBox type is a tuple struct with one element. That's why it looks like this, right? Tuple struct. That's why it's not, right? It's a tuple struct. That's why it looks like that. Usually we'd have, you're probably more familiar with looking at something like this, point, right? X, Y, right? But here it's a tuple struct with a single value. Okay. The myBox new function takes one parameter of type T and returns a myBox instance that holds the value passed in, X, right? Let's try adding the main function in listing 15.7 to listing 15.8 and changing it to use the myBoxT type we defined instead of box T. Okay, so what we'll do is I'll just comment this out so we can save it for later, and I will use myBox. Okay. Attempting to use myBoxT in the same way we used will result in an error. You can see right here, again, I don't need to compile. That's Rust Analyzer for you, right? Here's what it says. Type myBox integer cannot be dereferenced. Our myBoxT type can't be dereferenced because we haven't implemented the ability on our type. To enable dereferencing with the asterisk operator, we implement the deref trait. And we've implemented traits before. This isn't new stuff, right? We've done this, and look, it's like the book is talking through me. As discussed in chapter 10. So we're going to be treating a type like a reference by implementing the deref trait. As discussed in chapter 10, to implement a trait, we need to provide implementation for the trait's required methods. The deref trait provided by the standard library requires us to implement one method named deref that borrows self and returns a reference to the inner data. In the listing below, we see the implementation of deref to add to the definition of myBox. All right, so let's implement that. So we have our myBox here. This is the implementation there. We're going to create another implementation block, generic over type T, where we implement the trait deref for, and we specify the struct that we're implementing it for. And then here, we're going to say type target equals T, and then function deref, it's going to take itself, right, a reference to itself. It's going to return a reference to T. And it's going to do self.0 because that's how you access the first property of a tuple, right? If we had a tuple with two values, we could do this to grab the second one. That's all that's doing now. Okay, so what's happening? The type target T syntax defines an associated type for the deref trait to use. Associated types are a slightly different way of declaring a generic parameter, but you don't need to worry about them for now. We'll cover them more in chapter 19. All right, I'll take it for granted. Oh, what does this say? Let's just see this real quick. Cannot find trait deref in the scope, not found in the scope. So you see here we need to import the trait so we know what we're implementing. Let's do that up here. There we go. Okay. We fill in the body of the deref method with a reference to self.0. So deref returns a reference to the value we want to access with the asterisk operator. So this is key. It doesn't return the value. It returns a reference to the value so that using the asterisk operator on the return value will work, because what does the asterisk work on? References. It's pretty cool, right? The main function that calls the dereference on mybox_t value now compiles and the assertions pass. So let's try it. Awesome. So again, instead of returning self.0, if we return self.0, this would be redundant. We return the reference so that this works. Pretty cool. The reason the deref method returns a reference to a value, I swear I didn't read ahead. I didn't, promise. The reason the deref method returns a reference to a value and that the plain dereference outside the parentheses in y deref is still necessary. Oh, that's interesting. Is the ownership system. If the deref method returned the value directly instead of referencing to the value, so this is the code it actually ran. This is key, right? Love that. Okay, so we fill in the body of deref with &0. So deref returns a reference to the value you want to access with the asterisk operator. The main function calls star on the mybox value now compiles. Without the deref trait, the compiler can only dereference standard references, right? The deref method gives the compiler the ability to take a value of any type that implements deref and call the deref method to get the & reference that it now knows how to dereference with the asterisk, right? Makes sense? So we entered asterisk y to dereference y, but behind the scenes, Rust called the deref function, which gave it back a reference, and therefore the asterisk works, right? So Rust substitutes the asterisk operator with the call to deref method, then a plain dereference, so we don't have to think about whether or not we need to call the deref method ourselves. This Rust feature lets us write code that functions identically whether we have a regular reference or a type that implements dereference, such as box. Pretty cool. The reason the deref method returns a reference to a value and that the plain dereference outside the parentheses in asterisk deref is still necessary is the ownership system. If the deref method returned the value directly instead of a reference to the value would be moved out of self. So that's key. The reason it doesn't return the value directly is the value would be moved out of self. Self wants to maintain ownership, right? Your box wants to keep ownership, so that's why it returns a reference. That's super, super cool. That's awesome. We don't want to take ownership of the inner value inside mybox_t, in this case or in most cases where we use the dereference operator. Note that the asterisk operator is replaced with a call to the deref method and then a call to the asterisk operator just once each time we use the asterisk in our code. Because the substitution of the asterisk operator does not recurse infinitely, we end up with the data of type signed 32-bit integer, which matches our assertion. That's pretty cool. All right. Implicit deref coercions with functions and methods. Deref coercion is a convenience that Rust performs on arguments to functions and methods. Deref coercion works only on types that implement the deref trait. So it'll work on our mybox because we implemented the deref trait. Pretty cool. Deref coercion converts such a type into a reference to another type. For example, deref coercion can convert a reference to a string slice because string implements the deref trait such that it returns string. Pretty cool. Deref coercion happens automatically when we pass a reference to a particular type's value as an argument to a function or method that doesn't match the parameter type in the function or method definition. I'm going to read that again because that's key, right? Deref coercion happens automatically when we pass a reference to a particular type's value as an argument to a function or method So we pass it as an argument to a function method that doesn't match the parameter type in the function or method definition. A sequence of calls to the deref method converts the type we provided into the type the parameter needs. Deref coercion was added to Rust so that programmers writing function and method calls don't need to add as many implicit references and dereferences with the asterisk and the ampersand. The deref coercion feature also lets us write more code that can work for either references or smart pointers. So I like that. So you don't need to think about, it allows you to write your code in a way where you don't really care what type of pointer it is. You're going to use dereferencing in the same way regardless of whether you're dealing with a smart pointer or a standard reference. So that's pretty cool. To see deref coercion in action, let's use the mybox type we defined in the previous listing, as well as the implementation of deref that we added. So below, we see the definition of a function that has a string slice parameter. All right, let's create it. So our function hello. Function hello takes a name that is a string slice. And we're going to print ln. Like classic hello world. Name. We can call the hello function with the string slice as an argument such as hello Rust. For example, deref coercion makes it possible to call hello with a reference to a value of type myBoxString as shown in listing 15.2. So let's try that out. So let's do let m equal mybox new string. This is a standard string, right, from Rust. And then we're going to call hello with a reference to m. And if I run that, there we go. You see it still works. And we'll change that to hello Twitch and YouTube. Pretty cool. Here we're calling the hello function with the argument ampersand m, which is a reference to m. It's a reference to the mybox string value. Because we implemented the deref trait on mybox t in listing 15.10, Rust can turn the reference to the mybox string into a reference to a string by calling deref. The standard library provides an implementation of deref on string that returns a string slice, and this is in the API documentation for deref. Rust calls deref again to turn the reference to a string into a string slice, which matches the hello function signature. So we can pass, even though this is recommending a string slice, you can also think of this as a reference to a string. And so we have because we have a mybox of type string that implements the deref, this will actually work, right? And again, it's because Rust can turn a reference to a mybox string into a reference to a string by calling deref, and the standard library provides an implementation of deref on string that returns a string slice, and this is in the API documentation for deref. Rust calls deref again on that reference to a string to convert it into a string slice, and therefore it matches. And it does it itself, right? That's the coercion part. We didn't do it manually. Okay, so here we have the code we would have to write if we didn't have coercion. So what would we have to do? We'd have to call hello with the reference to the dereferenced m, and then converting it into a string slice using this, right? The asterisk m dereferences the mybox string into a string. Then the ampersand and the brackets with the dot dot take a string slice of the string. It takes a slice, right? That is equal to the whole string to match the signature of hello. That's why we have dot dot. You know that usually if we want to take a particular piece, we'd specify the indices. But dot dot will give us the whole string. The code without deref coercion is hard to read, write, and understand. That is for sure. With all of these symbols, right? Deref coercion allows Rust to handle these conversions for us automatically. So it allows us to write much nicer code, much easier to read. When the deref trait is defined for the types involved, Rust will analyze the types and use the deref as many times as necessary to get a reference to match the parameter's type. That's pretty awesome. The number of types that deref needs to be inserted is resolved at compile time, not runtime. So there's no runtime penalty for taking advantage of deref coercion. So I think that's a sign. They're just saying, do it, use it. And absolutely, that's very cool. It makes it so much easier to read, which is fantastic. Okay, how does deref coercion interact when we're dealing with mutability? Again, the ability to mutate or change values, right? Similar to how you use the deref trait to override the asterisk operator on immutable references, you can use the deref mute trait to override the asterisk operator on mutable references. Rust does deref coercion when it finds types and trait implementations in 3 cases. So from a reference to a generic type T to a generic type U, when T's dereference is generic over the target U. From a mutable T to a reference to a mutable U, when T's dereference mutable is generic over a type target, where target is equal to the type U. From a reference to a mutable T generic to a, so in this case, we're going from mutable to a non-mutable reference, when, as long as the deref for T returns target U. So if you implement deref generic over target U, you can do both of these. The first 2 cases are the same except for mutability. The first case states that if you have a reference to T and T implements deref to some type U, you can get a reference to U transparently. Okay. The second case states that the same deref coercion happens for mutable references. The third case is trickier. Rust will also coerce a mutable reference to an immutable one, but the reverse is not possible. Immutable references will never coerce to mutable references because of the borrowing rules. If you have a mutable reference, that mutable reference must be the only reference to that data. Otherwise, the program wouldn't compile. So if you have a mutable reference, you can't have multiple. It can only be one. Converting one mutable reference to one immutable reference will never break the borrowing rules. Converting an immutable reference to a mutable reference would require that the initial immutable reference is the only immutable reference to that data. But the borrowing rules don't guarantee that. Therefore, Rust can't make the assumption that converting an immutable reference to a mutable reference is possible. What does all that mean? Basically, what it's saying is if you have an immutable reference, it can be the only reference. Sorry, if you have a mutable reference, it can be the only reference because it's mutable, right? If you have other references and you change that data at some point, those other ones are invalid, so they don't allow you to have multiple. And it says here, Rust can't make the assumption that converting an immutable reference to a mutable reference is possible because it doesn't know how much that mutable reference may be owned by many different places. So it can't convert it to mutable because it would break that rule that mutable references can only be owned by one, right? So pretty cool. Running code on cleanup with the drop trait. All right, let's dig in. Running code on cleanup with the drop trait. The second trait important to the smart pointer pattern is drop, which lets you customize what happens when a value is about to go out of scope. So at the end of the main function, for example, are all of these values, x, y, m, they all go out of scope at the end of this function, and so the drop trait is used for that. You can provide an implementation for the drop trait on any type, and the code you specify can be used to release resources like files or network connections. We introduced drop in the context of smart pointers because the functionality of the drop trait is almost always used when implementing a smart pointer. For example, when a box over generic type T is dropped, it will deallocate the space on the heap that the box points to. In some languages, the programmer must call code to free memory or resources every time they finish using an instance of a smart pointer. C, I'm looking at you because this was confusing when I was learning it in school and I wasn't getting as much nice detail as this book. We didn't have this resource. Twitch wasn't around. I was learning from my professors. They were talking about this stuff and I was failing, so I was drawing in my notebook and not paying attention. But we're here now. We're paying attention. We're not dealing with C, so I'm excited. All right. In some languages, you have to free it up yourself, right? If you forget, the system might become overloaded and crash. Happened all the time to me. Just gonna admit it. In Rust, you can specify that a particular bit of code be run whenever a value goes out of scope, and the compiler will insert this code automatically. As a result, you don't need to be careful about placing code cleanup or cleanup code everywhere in a program that an instance of a particular type is finished with. You still won't leak resources, right? Specify the code to run when a value goes out of scope by implementing the drop trait. We saw how we implemented the deref trait. Now we're going to see how to implement the drop trait. The drop trait requires you implement one method named drop that takes a mutable reference to self. To see when Rust calls drop, let's implement drop with println statements for now so we can see when it's happening. Okay, so the listing below shows a custom smart pointer. Let's create a new project for this. All right. Source main. All right, let's copy this code here. So we're going to create a struct. All right. So we're going to implement drop for custom smart pointer with a function drop that takes a mutable reference to self. And right now it's just going to print dropping custom smart pointer with data. All right. And in our main function, we're going to create some custom smart pointers. Okay. So let C equal custom smart pointer. Data is going to be string from my stuff. Then we'll have let D equal custom smart pointer. It'll contain data that's going to be string from other stuff. And then print ln custom smart pointers created. Right? Okay. A custom smart pointer struct that implements the drop trait where we would print our cleanup code. The drop trait is included in the prelude. Remember, the prelude is what Rust brings in by default. So we don't need to bring it into scope. We implement the drop trait on the custom smart pointer and provide an implementation for the drop method that calls println. The body of the drop function is where you would place any logic that you wanted to run when an instance of our type goes out of scope. We're printing some text here to demonstrate when Rust will call drop. In main, we create two instances of the custom smart pointer and then print custom smart pointers created at the end of our main. Our instances of custom smart pointer will go out of scope, and Rust will call the code we put in the drop method, printing our final message, right? So when they get dropped, it should print the message. So let's run it and see what happens. So you can see here, we're not using D, that's why it said this, but you can see here, custom smart pointers created, and then dropping custom smart pointer with data, other stuff, and my stuff. So pretty cool. I think that's pretty cool. All right. Rust automatically called drop for us when our instances went out of scope, calling the code we specified. Variables are dropped in the reverse order of their creation. That's pretty interesting. So you can see that it was dropped in the reverse order. So other stuff got dropped first. We did see that. That's pretty cool. That's really interesting. So they're dropped in the reverse order that they were created. So D was dropped before C. The example gives you a visual guide to how the drop method works. Usually you would specify the cleanup code that your type needs to run rather than print a message, right? You clean it up. Dropping a value early with standard memory drop. Unfortunately, it's not straightforward to disable the automatic drop functionality. Disabling drop isn't usually necessary. The whole point of the drop trait is that it's taken care of automatically. Occasionally, however, you might want to clean up a value early. One example is when using smart pointers that manage locks. You might want to force the drop method to release the lock so that other code in the same scope can gain access to the lock. Rust doesn't let you call the drop method's trait directly. You can't just call drop. Instead, you have to call the standard memory drop function provided by the standard library if you want to force a value to be dropped before the end of its scope, right? Before the end of the function runs or whatever scope you're in. If we try to call the drop traits drop directly by modifying the main function below, we'll see an error. So we're not going to try that, but basically, if we tried to call drop, c.drop, that won't work. Explicit destructure call is not allowed. This error message states that we're not allowed to explicitly call drop. The error message uses the term destructure, which is the general programming term for a function that cleans up an instance. A destructure is an analogous to a constructor, which creates an instance. The drop function in Rust is one particular destructure. Does that make sense, right? Construct, destruct. Rust doesn't let us call drop explicitly because Rust would still automatically call drop on the value at the end of main. This would be a double free error because Rust would be trying to clean up something that's already cleaned up. We can't disable the automatic insertion of dropped when a value goes out of scope, and we can't call the drop method explicitly. So if we need to force a value to be cleaned up early, we can use the standard memory drop function. The standard memory drop function is different from the drop method in the drop trait. We call it by passing the value we want to force to be dropped early as an argument. The function is in the prelude, so we don't even need to pull it in. And so here, let's try dropping it early. So here we have C. We're going to print this. Move this here. Custom smart pointer created. Then we're going to call drop C. We're going to print custom smart pointer dropped before the end of main. All right, let's run this. Get out of your way here. And so what gets printed out? Custom smart pointer created, dropping custom smart pointer with data my stuff, custom smart pointer dropped before the end of main, custom smart pointer is created, dropping custom smart pointer with data other stuff. So you can see my stuff is actually dropped first here because we're manually calling that. So that's pretty cool. All right. No, we don't want live share. Okay, so let's go on. The text dropping custom smart pointer with data some data is printed between the creation and the drop at the end of main, showing that the drop method code is called to drop C at that point, right? We can use code specified in the drop trait implementation in many ways to make cleanup convenient and safe. For instance, you can use it to create your own memory allocator. With the drop trait and Rust's ownership system, you don't have to remember to clean up because Rust does it automatically, right? That's the beauty. We love that. You also don't have to worry about problems resulting from accidentally cleaning up values still in use. The ownership system that makes sure references are always valid also ensures that drop gets called only once when the value is no longer being used. Now that we've examined box T and some of the characteristics of smart pointers, let's look at a few other smart pointers defined in the standard library. All right, so we got reference counted smart pointer. In the majority of cases, ownership is clear. You know exactly which variable owns a given value. However, there are cases when a single value might have multiple owners. For example, in graph data structures, multiple edges might point to the same node, right? A single node, multiple things pointing to it. And that node is conceptually owned by all of the edges that point to it. A node shouldn't be cleaned up unless it doesn't have any edges pointing to it, right? You can't clean something up if there's still something referencing it. To enable multiple ownership, Rust has a type called reference counting over the generic type T, which is an abbreviation for reference counting. The reference counting type keeps track of the number of references to a value, which determine whether or not the value is still in use. If there are 0 references to a value, the value will be cleaned up without any references becoming invalid. So imagine reference counting T as a TV in a family room. When one person enters to watch the TV, they turn it on. Others can come into the room and watch the TV. When the last person leaves the room, they turn the TV off because it's no longer being used. If someone turns off the TV while others are still watching it, there would be uproar from the remaining TV watchers. Low-key, this has happened, right? Sometimes I left the TV on when I was a kid. My mom would be like, what are we, related to somebody at the electric company? I'd be like, oh, you're right. But this makes sense, right? You don't just walk in on your friends and shut it off. I mean, maybe you do. Maybe they're watching The Bachelor and you're like, off. Could happen. We use the reference counting type when we want to allocate some data on the heap for multiple parts of our program to read. And we can't determine at compile time which part will finish using the data last. If we knew which part would finish last, we could just make that part the data's owner. And the normal ownership rules we enforce would work, right? And they take effect. Note that reference counting is only for use in single-threaded scenarios. When we discuss concurrency in Chapter 16, we'll cover how to do reference counting in multi-threaded programs. All right, let's take a look. Using reference counting to share data. So first, because I know we're going to get into a little bit of reference counting stuff, I'm going to go ahead and create that. And let's just move this over here. Get rid of this. Get rid of this. Move this here. All right, so what do I want to do? I want to do cargo new reference counting. And what I could do is create a workspace for each of my chapters, and then I wouldn't have to worry about Rust Analyzer. So maybe we'll do that. Okay, reference counting. Let's return to our cons list example, right? Recall that we defined it using box T. This time we'll create two lists that both share ownership of a third list. Conceptually, this looks similar to the figure listed here. So we have B and C and A. A just points to its own list, but we have C pointing to A as well and B pointing to A. We'll create a list A that contains 5 and then 10. So that's this here. And then nil is the end, right? Then we'll make two more lists, B and C, that start with B starts with 3, C starts with 4. And both B and C will continue onto the first of A, containing the 5 and 10. In other words, both lists will share the first list containing 5 and 10. All right, so let's write this out. List, cons. So this is the same thing we had before, right? Cons 5, box, new, cons. So we have cons 5, and then it's going to contain box new, which is going to contain cons, which is going to have 10, and then box new, nil. All right, so this is just A, right? So A is a cons list that contains 5, then contains another cons list containing 10, and nil is where it ends. Now B is going to be a cons list that contains 3, and then A, right, in a box. And C is going to contain 4 and then A. So A is referenced by both B and C. Got it? All right. Demonstrating we're not allowed to have two lists using box T that try to share ownership of a third list. When we compile this code, we get an error. So let me save, and you'll see right here, I get the error because of Rust Analyzer. Use of moved value A, value used here after move. So it tells you on line 11, the value moved, and on line 10, move occurs because A has type list, which does not implement the copy trait. Cool. The cons variant owns the data they hold. So when we create the B list, right, A is moved into B and B now owns A. Then we try to use A again when creating C. We're not allowed to use it because A is moved, right? B has taken ownership. We could change the definition of cons to hold references instead, but then we'd have to specify lifetime parameters. By specifying lifetime parameters, we would be specifying that every element in the list will live at least as long as the entire list. The bar checker won't let us compile let a cons reference nil, for example, because the temporary nil value would be dropped before a could take a reference to it. Instead, we change our definition of list to use reference counting in place of box T as shown in listing 15.8. Each cons variant will now hold a value and a reference counter pointing to a list. When we create B, instead of taking ownership of A, we'll clone the reference counting list that A is holding, thereby increasing the number of references from 1 to 2 and letting A and B share ownership of the data in the reference counting list. We'll also clone A when creating C, increasing the number of references from 2 to 3. Basically, every time we call a reference counting clone, the reference count to the data within the reference count list will increase, and the data won't be cleaned up unless there are 0 references to it. That's a lot. Let's see what it looks like. So we're just going to change this to RC. And here, instead of calling box, right, we're going to call RC. Just change it to this. We also have to pull in RC. It's not in the prelude. And instead of using ref, instead of using A, we're going to use a reference to A. And in fact, we're going to call rc.clone instead of rc.new. Okay, let's see what we did here. We need to add a use statement to bring in the reference counting into scope because it's not in the prelude. In main, we create the list holding 5 and 10, that's A, right? And we stored it in a new reference counting list in A. Then we create B and C. We call reference counting clone function to pass a reference to the reference counting list in A as an argument. So we're passing a reference to the reference counting list in A as an argument. What is it saying? Expected reference standard reference list. Did I do this right? Clone A. Reference counting new. Reference counting list. A needs to be a RC new. There we go. All right, let's read that again. We bring in the use statement because it's not in the prelude. We then create the list holding 510 and store it in a new reference counting list. So we store that in an entire reference counting list in A. Then we create B and C and we call reference counting clone function and pass it a reference to A as an argument. We could have called A clone rather than RC clone reference to A, but Rust's convention is to use RC clone in this case. The implementation of reference counting clone doesn't make a deep copy of all the data like most types implementation of clone do. The call to reference counting clone only increments the reference count, which doesn't take much time. Deep copies of the data can take a lot of time. By using RC clone for reference counting, we can visually distinguish between the deep copy kinds of clones and the kind of clones that increase the reference count. When looking for performance problems in the code, we only need to consider the deep copy clones and can disregard the reference counting clone. Pretty cool. Closing a reference counter increases the reference count. Let's change our working example in listing 15.8 so we can see the reference counts changing as we create and drop references to the reference counting list in A. In listing 15.19, we'll change main so it has an inner scope around list C. Then we can see how the reference count changes when C goes out of scope. All right, I'm just gonna go ahead and keep this. We have A, we have B. Let's go ahead and add this print statement here. Count after creating A equals, and then we'll call RC strong count, interesting, and we'll pass it a reference to A. And then we're going to call after B, we're going to say count after creating B, and this is going to be strong count. We're still getting the count of A. And then we're going to create a scope that surrounds C. That's what this is doing here. And we're going to do print ln, similar to this, but for C. Creating C. And then here we're going to do count after C goes out of scope equals, and then we're going to call RC strong count on reference to A. All right. At each point in the program where the reference count changes, we print the reference count, which we can get by calling the reference count strong count function. This function is named strong count rather than count because reference count type also has a weak count. We'll see what weak count is used for in the preventing referencing cycles, turning a reference count into a weak section. All right. Alrighty. Okay, so here's what we're going to do. We're going to go ahead and run this. Let me get out of your way. Okay, so we see count after creating A, 1. Count after creating B, 2. Count after creating C, 3. Count after C goes out of scope, 2. So you see it goes down once it goes out of scope and is dropped. Pretty cool. All right. We can see that reference count list in A has an initial reference count of 1. Then each time we call clone, the count goes up by 1. When C goes out of scope, the count goes down by 1. We don't have to call a function to decrease the reference count like we have to call RC clone to increase the reference count. The implementation of drop trait, right, which happens automatically when something goes out of scope, decreases the reference count automatically for us. What we can't see in this example is that when B and then A go out of scope at the end of the main, the count is then 0 and the reference count list is cleaned up completely at that point. Using reference count allows a single value to have multiple owners, and the count ensures that the value remains valid as long as the owners still exist. So as long as that count's not 0, it needs to be valid, right? Via immutable references, reference count allows you to share data between multiple parts of your program for reading only. If reference count allowed you to have multiple mutable references too, you might violate one of the borrowing rules discussed in Chapter 4. Multiple mutable borrows to the same place can cause data erase and inconsistencies, right? If two people borrow a mutable reference, one can change it, right? And that can cause data inconsistencies. But being able to mutate data is very useful. In the next section, we'll discuss the interior mutability pattern and the refcell type that you can use in conjunction with a reference counting type to work with this immutability restriction. All right, let's see. We have half hour. I think we can get through this. If not, we'll just stop halfway through, but I think we'll be pretty far. All right, refcell and the interior mutability pattern. Interior mutability is a design pattern in Rust that allows you to mutate data even when there are immutable references to that data. Normally, this action is disallowed by the borrowing rules. To mutate data, the pattern uses unsafe code inside a data structure to bend Rust's usual rules that govern mutation and borrowing. We haven't yet covered unsafe code. That happens at the end. We can use types that use the interior mutability pattern when we can ensure that borrowing rules will be followed at runtime, even though the compiler can't guarantee that. The unsafe code involved is then wrapped in a safe API, and the outer is still immutable. Let's explore this concept. That's a lot. So let's explore this concept looking at refcell type that follows the interior mutability pattern. All right, enforcing borrowing rules at runtime with refcell. Unlike reference counting, the refcell type represents a single ownership over the data it holds. So what makes refcell different from a type like box, right? Recall the borrowing rules you learned in Chapter 4. 1. At any given time, you can have either, but not both, one mutable reference or any number of immutable references. References must always be valid. When a reference, so with references in box T, the borrowing rules invariants are enforced at compile time. With refcell T, these invariants are enforced at runtime. With references, if you break these rules, you'll get a compiler error. But with refcell, if you break these rules, your program will panic and exit. So it actually lets you go through with it, right? The advantages of checking the borrowing rules at compile time are the errors will be caught sooner in the development process, and there's no impact on the runtime performance because all of the analysis is completed beforehand, right before you run that code. For those reasons, checking the borrowing rules at compile time is the best choice for the majority of cases, which is why it's the default for Rust. All right, so why refcell, right? So the advantage of checking the borrowing rules at runtime instead of that certain memory safe scenarios are then allowed. So the advantage of checking the borrowing rules at runtime instead is that certain memory safe scenarios are then allowed, whereas they are disallowed by the compile time checks. Static analysis, like the Rust compiler, is inherently conservative. Some properties of code are impossible to detect by analyzing the code, right? So you can't detect everything just by reading it. The most famous example is the halting problem, which is beyond the scope of this book, but an interesting topic to research. I learned about that in what class is that? Discrete structures. It's an interesting problem. Knowing whether it's basically, a summary is it's knowing whether a given program will halt on input X, right? Look it up, out of the scope for the stream. All right, so let's see. The halting problem. Okay. Rust rejects the correct program. The program. Okay, so here we go. I lost my place. Guarantees that Rust makes. Okay, yeah. So some analysis is impossible. It can't make sure the code compiles, right? It's conservative. If Rust accepts an incorrect program, users will be able to trust the guarantees Rust makes. However, if Rust rejects the correct program, the programmers will be inconvenienced, right? So there's a balance there, right? Nothing catastrophic can occur. The rest cell type is useful when you're sure your code follows the borrowing rules, but the compiler is unable to understand and guarantee that. So you're sure it follows it, but the compiler can't, by just doing a static analysis, it can't determine that. So similar to reference counting, rest cell is only used for single-threaded scenarios and will give you a compile time error if you try to use it in multi-threaded context. We'll talk about this when we get to that functionality in chapter 16. Here is a recap of the reasons you choose box T, reference counting T, and ref cell. Reference counting enables multiple owners of the same data. Box T and ref cell have single owners. Box T allows immutable and mutable borrows checked to compile time. Reference counting allows immutable borrows checked to compile time. Only immutable, right? Ref cell allows immutable borrows checked at runtime. Because ref cell allows mutable borrows checked at runtime, you can mutate the value inside a ref cell even when the ref cell is immutable. That's wild. I don't know about that. Mutating the value inside an immutable value is the interior mutability pattern. That's where we expose a public API that lets you mutate it, right? Let's look at a situation in which interior mutability is useful and examine how it's possible. All right, interior mutability. So we'll just do it down here. What is this? Reference counting. So you know what we'll do? This is all about ref cell? Yeah, it's all about ref cell. So we'll create another one. I save this. All right. Let's go ahead and write this code out. So we have let x equal 5, let y equal immutable reference to x. If you try to compile this code, you'll get the following error. We can see it here. Cannot borrow x as mutable, as it is not declared as mutable, right? It's declared as immutable. However, there are situations in which it would be useful for a value to mutate itself in its methods but appear immutable to other code. Code outside the value's methods would not be able to mutate the value. Using ref cell is one way to get the ability to have interior mutability, but ref cell doesn't get around the borrowing rules completely. The borrow checker in the compiler allows this interior mutability, and the borrowing rules are checked at runtime instead. If you violate these rules, right, your program will panic instead of showing a compiler error. Let's work through a practical example where we can use ref cell to mutate an immutable value and see why that's useful. A use case for interior mutability, mock objects. For test, right? A test double is the general programming concept for a type used in place of another type during testing. Mock objects are specific types of test doubles that record what happens during a test so you can assert that the correct actions took place. That's pretty cool. Here's an example. If you've ever used JavaScript testing frameworks or Python, you might have a function, right? A stub function, or what we would call a spy. And so a spy is a mock implementation of a function that just indicates whether or not said function was called. So let's imagine you have a test. You're testing a function that should compute the average of an array of numbers. And it does that by calling an add function, or it calls a sum function that takes an array and sums it, right? You need to do that first before you can get the average, right, or the mean, right? Because you would sum the list and then you divide it by its length. So let's assume you create a function that sums the list. You can create, when you're testing, a spy function on that add, so that you don't need to have that add function there. You create a spy on add, and you just ensure that that function is called. And you can write that mock function to return some fixed result, and it'll just indicate to you whether or not it was called. So that's similar here. That's something we also call that a test double, right? Rust doesn't have objects in the same sense as other languages have objects, and Rust doesn't have mock object functionality built into the standard library as some other languages do. However, you can definitely create a struct that will serve the same purposes as a mock object. Here's the scenario we'll test. We'll create a library that tracks a value against the maximum value and sends messages based on how close to the maximum value the current value is. This library can be used to keep track of a user's quota for the number of API calls they're allowed to make, for example. So if you're rate limiting, right? Our library will only provide the functionality of tracking how close to the maximum value is and what the messages should be at what times. Applications that use our library will be expected to provide the mechanism for sending the messages. The application could put a message in the application, send an email, send a text message, or something else. The library doesn't need to know that detail, right? All it needs is something that implements a trait we'll provide called messenger. Okay, let's try it out. All right, so we're going to create let's just change this to lib. And we'll create a public trait. Messenger. It's going to have a function called send, which takes the mutable self. A message, which is a string slice. Public struct called limit tracker. So what we're saying here is we're defining a trait messenger. Something has the trait messenger if it implements a send function. So here we're going to create a struct called limit tracker. Again, this is a lifetime A, right? And it's going to take type messenger. So it's taking a generic type as long as that type implements a send function. And so you have your messenger, which is a reference. We have lifetime reference to T. Value, which is a usize, because it's a usize always represents an index of a list or a size of a list. Max is a usize. All right, so we're gonna have our implementation block here. Implement a T limit tracker a T where T is of type messenger, implements trait messenger, right? And that, and what we're gonna do is public function new messenger, so you pass it a messenger, and it's a reference to that type, a max, which is gonna be usize. We're gonna return a new limit tracker of type T, right? So new turns limit tracker of type T, and we're going to create that limit tracker. We're going to just use messenger as its messenger, set its value to 0, and its max to max, and we can just use this shorthand for that. All right, next we need a function called set value, which takes the mutable self a value, which is a usize. And here what we're going to do is we're going to say self.value equals value. So we're going to manipulate that. And then let percentage of max equals self.value as a 64-bit integer divided by self.max, or 64-bit float, right? Because we're doing division. That's the percentage. And then I'm just going to copy this because I don't want to type this whole thing. So if percentage of max is greater than or equal to 1, so you're over your quota. If it's greater than 9, you've used up 90% of your quota. And if it's greater than 0.75 but less than 9, right, you've used up over 75% of your quota. And this here, it says, let's see, expectant item. That's something up here. No, this looks right. Oh, I spelled this wrong. All right, and what did I do here? Limit tracker, max, that's all right, that's right. This is saying expected bang. I guess because it's expecting a macro, let's see. Public function, oh, I forgot function. There we go. Okay. One important part of this code is that the messenger trait has one method called send that takes an immutable reference to self and the text of the message. This is the interface our mock object needs to have. The other important part is that we want to test the behavior of the setValue method on the limit tracker. We can change what we pass in for the value parameter, but setValue doesn't return anything for us to make assertions on. It just changes the value. We want to be able to say that if we created a lifetime tracker with something that implements the messenger trait and a particular value for max, when we pass different numbers for value, the messenger is told to send the appropriate messages, right? We need a mock object for that. Instead of sending an email or a text message when we call send, we only keep track of the messages it's told to send. We can create a new instance of the mock object, create a limit tracker that uses the mock object, call the setValue method on said limit tracker, and then check that the mock object has the messages we expect. So we're not going to send anything, we're just going to store them, right? So below shows an attempt to implement a mock object to do just that, but the borrow checker won't allow it. Okay, let's see. So we're going to create mod. I'm just going to copy this. It's a lot here. And we'll just walk through it. Okay. So we're creating our test, mock messenger. Sent messages, just a vector. Here's its implementation, a new mock messenger. Here's its implementation of send, which we know we need because it's a type messenger trait, right? And it's just going to push the message onto our vector so we can inspect it. And then in our test, we just check that it sends the correct message. What do? We create a limit tracker with a value of max, and we check that it sent one message. Right? We check the length is 1, and so forth. So this test code defines a mock messenger struct that has a sent messages field with a vector string, keeps track of the messages that are sent to it. We also define an associated function new to make it convenient to create a new mock messenger value that starts with an empty list of messages. We then implement the messenger trait for the mock messenger so we can give a mock messenger to a limit tracker. In the definition of the send method, we take the messages passed and just pop them into that list of sent messages on the mock messenger. In the test, we're testing what happens when the limit tracker is told to set the value to something that is more than 75% of the max value. First, we create a new mock messenger, which we start with an empty list of messages. Then we create a new limit tracker and give it a reference to the new mock messenger, so it uses that, and a max value of 100. We call the setValue method on the limit tracker with a value of 80, which is more than 75% of 100, but less than 90. So we get that third arm there. Then we assert the list of messages that the mock messenger is keeping track of should now have only one message in it. Because if we put, 1, it would be greater than all of these, and all 3 would send, right? So that makes sense. So we get an error though. Can't borrow self.sentMessages as mutable as it's behind a reference. We can't modify the mock messenger to keep track of the messages because the send method takes an immutable reference to self. We also can't take the suggestion from the error text to use mutable self instead, because then the signature of send won't match the signature of the messenger trait definition. Feel free to try and see what error message you get. All right, let's run it. Just gonna run cargo test. I'm gonna move out of your way here. Duplicate definitions for new. Oh, why is that? Okay, I have limit tracker. Did I redefine limit tracker accidentally? Ah, yeah, so I accidentally redefined when I copied these. Let me get rid of these. All right. Here you can see cannot borrow as mutable. So we get the error right there without even having to compile it. Okay. So here, this is a situation in which interior mutability can help. We'll store the sent messages within a ref cell T. And then the send messages will be able to modify send messages to store messages we've seen. All right, let's see what that looks like. So we're going to pull in use standard cell ref cell. And then here, instead of a vector, we're going to say ref cell of type vector. And then here, when we create new ones, we're going to have to say ref cell new. And here, when we're pushing, we need to call sent messages dot borrow mute, which I'm sure we'll see what that is in a second. Push. And then here we grab the length. It's already telling us down here we need to do borrow immutable len. The send messages field is now type ref cell vector string instead of vector string. In the new function, we create a new ref cell vector string instances around the empty vector. For the implementation of the send method, the first parameter is still immutable borrow of self, which matches the trait definition. We call borrow mute on the ref cell, which is happening here, right? So we call borrow mute on the ref cell. What up, Does in the chat? Poggers, what up? So we're going to call borrow mute on the ref cell in self.sendMessages to get a mutable reference to the value inside ref cell vector string, which is a vector. Then we call push on the mutable reference to the vector to keep track of the messages sent during the test. So that's what's happening here. We're pushing on the message. The last change we have to make is in the assertion. To see how many items are in the inner vector, we have to call borrow on the ref cell to get an immutable reference to the vector. Now that you've seen how to use ref cell, let's dig into how it works. Woo! All right, let's see where we're at. All right, I think we're gonna call it here because we'll get into how it works. I think next week we'll put that up because we still have this to get through, and then once we're done with this, we still have a few more parts in chapter 15, and we're already almost at time. So we're gonna give it an end here. Pretty intense stuff. I think it's pretty cool. Smart pointers are awesome. Box is definitely something we're gonna use. I've used that a bunch. Ref cell, I'm still intrigued. I can see why it's useful for this case, but yeah, it's pretty cool. Pretty awesome stuff. Really, I think it's very interesting learning about how the deref trait works. Like I loved learning about the deref trait and how, if I could pull it back up, how you return a reference that it can be used and how you can still use asterisks on it. I thought that was pretty cool. But yeah, anyway, so we're going to end it there. We'll look back into how ref cell works behind the scenes next time. And then we'll check out chapter 15.6 and wrap up chapter 15. Again, I will not be streaming next Tuesday. I'm getting some work done in the office, new carpet put in, new digs. You gotta upgrade, right? So that's gonna be happening, but I will be putting up a video on YouTube for those watching on YouTube. Maybe something different. I think I'm gonna do make an API request with Rust. So I'm reading about that, so I'll probably put that up. So I'll try to get that up by Tuesday, so you have something to watch on Tuesday or Wednesday when you normally watch on YouTube. So This will be posted as usual. Where's it going to go? You all know it already. It's going up on the YouTube. So I'll have this video posted either tomorrow afternoon or early Thursday. I've been trying to get it up on the following day, so I'm trying to get it up tomorrow afternoon. It uploads in standard def and then high def, so you'll see it there. Again, if you missed any chapters, if this was kind of like, whoa, what's going on? Just check out the previous chapters if you want. You can watch them at whatever speed you want there on YouTube. As always, follow on Twitter for getting notifications for when I go live. And I'll push this code up to our Learn Rust Live repo. So that is it for tonight. Thank you for those that attended the stream. Thank you if you're watching on YouTube. Again, feel free to leave comments below if you have any questions about anything. If you want to talk about anything or give suggestions for other videos or other content, feel free to do so. And once again, thank you to everyone who's been following and subscribing and watching on YouTube. It's really been fantastic to see all the great comments flooding in. I really appreciate them, and all the great views, and just, you know, it's fun going on this ride together with all of you. And, you know, we'd be happy to have you on the stream. The stream's been kind of weak lately. We can get a few more people in here. Those boys in the stream right now. We got Clam Watson. So yeah, join the stream Tuesdays 9 p.m. to 11 p.m. I'll be adding more in the future, or, you know, trying to do some other random days where I'll hop on and stream something smaller and not like a full 2 hour of the book. So keep that in mind. You can follow on twitch.tv/TomMcGurl. But yeah, I've had an awesome time. Again, we'll continue with 15.6 in 2 weeks. So keep an eye out. Thank you for joining tonight. If you joined live on the stream, if you're watching on YouTube, thanks again. I'm heading out. Have a great night.